Tonight's podcast should be fairly short. We just have one thing to finish up with calculated values for enthalpy. It's going to be number 3, and it's going to be bond dissociation. Sometimes I think your book just refers to it as bond enthalpies, so let's refer to it as bond enthalpies as well. So bond enthalpies, and they are just BE in your book. And we pretty much use this way of calculating delta H when or if delta HF standard is unknown. And this happens sometimes, alright? But this is the least accurate way to calculate delta HF. And we're actually going to use the same equation we finished with last night of methane is a gas, is combusted in oxygen in a gas to form carbon dioxide and water. I think that's balanced 2 to 2. And just in your notes, if we think back to just solving for delta H last night, pretty much every time in chemistry, whenever we have delta, it means final minus initial. In the case of last night, when we solved for delta H of F's, we have products minus reactants, which if we talk about a chemical equation, what do we end up with? Or what's our final products minus our reactants, which is what we begin with. So final minus initial is always what delta means, except for here. Okay? So in bond enthalpies, asterisk, star, whatever, but this is going to be initial minus final. And it's, I think, the only time in chemistry where this happens, so just be aware of that. It's a question that crops up again every 2 to 3 years on the AP test. It's an easy way to catch to see if you learned this, because I imagine a common answer is the reverse sign of what you should be getting, because it's initial minus final, not final minus initial. Okay? And the way that works is our delta H of reaction, formation of reaction, is going to equal the sum of the bond enthalpies of bonds broken minus the sum of the bond enthalpies of bonds formed. And because bonds broken are our reactants, and we're forming new bonds in our products, it ends up being initial minus final, or reactants minus products. Okay? For these particular problems, your best, the way to get started is to draw Lewis structures of everything. Okay? So CH4 looks like this. We have C bonded to 4 H's. Plus, we have oxygen, and oxygen is a double bonded O. Alright? And I would just go ahead and draw this as well. We have 2 oxygens, so we're going to draw this twice. And this yields carbon dioxide, and carbon dioxide is a double bonded O, double bonded O to a C, to a double bonded O. Alright, we have one of those. Plus water, which is O, happens to be a bent molecule. It's not that important that you draw it bent here, but we do have 2 waters. So I'm just going to draw 2 bent waters. If we're going to put lone pairs, we could. We don't have to. But here's our Lewis representation of this, what's happening. Okay? The way that these work is if you, again, look in your notes or your textbook, if you go to table 9.4, I don't think this is in the appendix, so this is pretty much the only table you're referring to. But some bond enthalpies of diatomic molecules, and here's the ones they list. This would have to be given to you on an AP test or a test of mine. But these bonds, so an HH bond requires 436.4 kilojoules per mole to break that bond. Okay, they're all listed as positive because this is always bond breaking. Okay, how much energy does it take to break these? If this bond is formed, what happens when bonds are formed? They give off energy. And again, we talked about this in our bonding unit. Notice A CC single bond, 343. A double bond requires more energy. It also requires more energy to break that bond, and then a triple bond requires even more energy. And then don't forget, or just be cognizant of this, but we have a C double bond O, and CO2 is different than a regular C double bond O, which is 745, but it's 799 for carbon dioxide. All right, so as we go back to this, if we look at our reactants, okay, so we're just going to set up our equation here. We have several different bonds. We have 4 CH bonds. Okay, how does that happen? We have one here, one here, one here, one here. Okay, we also have 2 O double bond O bonds. All right, and we're going to subtract. Okay, we have a couple CO bonds, and how many do we have? We have 2 of them. So we have one on the left, one on the right. And we have some OH bonds. And how many of those do we have? We have 2 in each molecule, but we have 2 molecules. So we really have 4 of those. That should be a plus sign. Alright, and now if we look on our table, we're going to find that CH bonds are 410 kilojoules of energy to make. And our OO bonds are 499 kilojoules to make. And we're going to subtract then out 2 COs, which we already said were 799, and then we have 4 OH bonds in our waters, and those OH bonds are 460. Alright, and when we do this math, we find that this comes out to negative 800 kilojoules per mole. If you refer to your notes from yesterday, we'll see whenever we calculated this out using heats of formation, we got a number that was closer to 890 kilojoules. Okay, and again, this is the least accurate way. Bond enthalpies is the least accurate way to calculate, but it gives us a pretty good ballpark. And usually it's within 10% of what a calculated value that's a little more accurate would be. Okay, so not as accurate, but it's pretty good. A lot of the inaccuracy comes from if we break one of these OH bonds. So if we were to sever this first one, it takes a certain amount of energy. But what's going to happen to break the second one? Because this is gone, this becomes a little more polar, and this oxygen wants this H a little more strongly. So our second bond, even though we would say an OH bond is 460, the second one's probably going to be closer to 480, 490. Okay, so this is going to jump up a little bit. Likewise over here, this first CH is going to be 410, our next one might be 420, 430. So subsequent bonds that break, usually that bond enthalpy goes up a little bit, which gives us this error amount. But again, we're typically within 10%. And that is it tonight. It's a short podcast. And that's it. Bond enthalpies. The big thing, be super just aware of this. It will probably catch you on the test. It catches students on the test that you'll have next week. Even though I'm saying know this, know this, know this, know this. Okay? So no bond enthalpies are initial minus final, or reactants minus products. And that's it.